I welcome Simone Silvestri.
How do I connect this? Black magic, who is this? Okay. Okay. So today I want to talk a bit about the current state and the future development and vision of the ClimaOcean package, or as I like to describe it, a Julia framework for building climate models. Now, this package is developed within the Climate Modeling Alliance, or CLIMA project, which, for who doesn't know, is collaboration between MIT and Caltech that has as the objective to develop a Julia native climate model. So in theory, this model is supposed to be able to learn from data, and as such to reduce significantly the uncertainty on future climate projections. And CLIMA is quite a big project, so it's very present in the Julia ecosystem. There are a lot of packages under the CLIMA organization. And here I'm showing just the major ones. So there is our atmosphere and land model, ClimaAtmos and ClimaLand, that depend on the CLIMA core package. That is a library for spectral element discretization on boxes or spheres. And these packages, these components are coupled through the CLIMA coupler to the ocean sea ice components, oceananics and sea ice, which are the components that we develop at MIT, and now also in Italy, and through other collaborations. And so arguably the most successful package of the CLIMA ecosystem is Oceananigans, is a flexible solver for fluid dynamic problems. So it allows you to build and construct simulations from idealized to realistic of ocean-flavored fluid dynamics. But today I really want to focus on the ClimaOcean component, and how the scope of this package changed throughout last year. So to remind what ClimaOcean is and what the scope of ClimaOcean was, this is a slide I presented last year at the last JuliaEO. So ClimaOcean was in its infancy then, it was a newborn. And the idea behind ClimaOcean was to try to provide a coupled ocean sea ice model to the Clima project. So arguably we could have done this within the Oceananigans library, because Oceananigans is very flexible and can do a wide range of simulations, but in itself, in its own right, it's an ocean model. So we could have done the coupling through Oceananigans, but we decided that a new package was the way to go for mainly two reasons. Because first of all, we wanted to keep the scope of the Oceananigans package very broad. We didn't want to bloat it with all the features that are necessary to specifically do simulations of the Earth, which is a very specific type of simulation. And because the CIS package that we started to develop right about the same time was developed in a new package, Clima CIS, that itself depends on Oceananigans. So the coupling couldn't really happen within the Oceananigans package. So we decided that a new package was the way to go, and we decided to call this new package ClimaOcean. And this name ClimaOcean was quite fitting for the package, because typically the coupling between a sea ice model and an ocean model is very tight in climate models. So typically the ocean and the sea ice run on the same grid, and the interface fluxes between the sea ice and the ocean are quite simple when it comes to interface fluxes, even if you compare it with what you need to couple the atmosphere with the other components. And for this reason, typically the sea ice model is embedded in the source code of many ocean models. For example, MIT GCM has its own sea ice package. NEMO has its own sea ice package, but these models are not called ocean sea ice models, they're called ocean models. So we thought ClimaOcean is the right name for this new package, because the only scope was to provide an ocean sea ice model to the Clima group. And for this scope, the package was supposed to be very, very lightweight. So we just needed a wrapper around an Oceananigans hydrostatic free surface model, which would provide the ocean simulation, a wraparound the Clima sea ice model, so a sea ice simulation method that will provide the sea ice, and a way to interface the two, so a method to compute the fluxes. And these would run on the same grid, and we would have an ocean CS model to ship to the Klima project. But throughout the year, last year, we also decided that KlimaOcean was the place where we would implement, where we would pursue another scope that was a little bit different from coupling with Klima, which is to perform a NOMIP simulation. So this is a standardized ocean simulation that is typically done when you build a new ocean and sea ice model. And it consists of 6 repeated cycles of 60-year forcing. This forcing specifically comes from an atmosphere that's provided from reanalysis data, which in this case is the Japanese reanalysis data. And what you do is you do these 6 cycles, then you take the last cycle and you compare it with observations or with other models, and you can assess the quality of your results. So to do this type of simulation, we have other requirements than the one that we need just to couple with the Klima model, because now we need an atmosphere. This atmosphere is just data that we need to download. This data is not on the same grid as the grid that we use for the ocean and the sea ice. So we need to regrid that data on the grid of the ocean. And we need a method to compute the fluxes between the atmosphere that we have from data and the ocean and the sea ice. Now, here we were at a crossroad. So we can achieve this in 2 different ways. So the typical way to perform the simulation is you download the data offline, you regrid it, you prepare it, and you use it to force your simulation. Then you build your simulation in your small package, you produce your results, you publish your paper, and that's it. And you've done your simulation. But when we saw these requirements, we thought that there's an opportunity here to do something a little bit more. Let's say that we want to change the ocean grid, for example. We don't want to have to re-download all the data, regrid it again, and restart the simulation, right? So we want to have flexible methods that allow us to specify an atmosphere, compute the fluxes between the atmospheres and the other components, to change the grid. And if we do that, which is arguably a little bit more work, now we end up with a package that looks a little bit more like a climate model already. It's not necessarily a climate model because we only have 3 components. We have an ocean, atmosphere, and sea ice. So we're missing a land, we're missing biogeochemistry, we're missing atmospheric chemistry, we're missing land ice, glaciers, and so on and so forth. But this structure resembles a little bit what climate models used to be at the beginning, an atmosphere, an ocean, and sea ice. So this is where the scope of the package kind of changed. We said, okay, well, we have this requirement. Let's not just provide an ocean sea ice model and have a wrapper. Let's expand a bit the scope of the package to be able to have something that looks more like an Earth builder. So the vision behind this package was to provide a framework where you could actually swap components in and out and build different climate simulations, just like Oceananics is a framework to build ocean simulations. So the idea behind Oceananics is that you can build idealized or realistic simulations of the ocean. Well, the idea for KlimaOcean would be to build idealized or realistic simulation of the climate, swapping in and out different components. And so I really like the quote from Milan about playing atmospheric modeling like it's Lego. And I thought that it was really fitting for the vision of KlimaOcean. And I didn't get the memo that you already changed to climate, but I guess we have aligned objectives now. So the idea is to have really a package that plays climate modeling like it's Lego, so you can swap in and out different components. So the key features that we need to have to achieve this goal is that we need to have swappable components. So these components need to be low complexity, intermediate complexity, full complexity, or whatever you want, prognostic, dynamic, or driven by data. So we need to have flexibility in how we compose our climate model. And most importantly, we want this model to be a home for surface parameterizations. So just like Oceananics is a little bit of a sandbox for users or ocean modelers to implement, test, and prototype new ocean parameterizations, we want this package to become a little bit of a sandbox for scientists that study the interface between atmosphere and ocean or ocean and other components to be able to implement, test, and prototype different surface parameterizations. And you'll notice that in the title, I have a question mark on the KlimaOcean name. And this is because clearly with this vision, the KlimaOcean name does not really fit the scope of the package. So we are in a quest for changing the name of the package into something more suitable, but we haven't really converged to a nice name, a name that we like. So it's something that we have to do within the next month. So this is kind of a little bit the vision of what we want to achieve. And now the the idea is how do we design a framework that allows you to build climate models? So what are climate models? And there are several different types of approaches for climate modeling or approaches to build climate models. And here I'm showing what I think are two different approaches. So on the left, there's the schematic of the EC Earth model. This is a climate model that's developed in Europe. It's a collaboration of a consortium between a lot of different European countries. I think there's Finland, Sweden, Norway, Italy, Germany, Ireland, Portugal, Spain. So it's what we call a little bit a Frankenstein model, because the consortium does not really develop the components, but it takes already developed components from different modeling centers and unifies them in one Earth system model through a flexible coupler can put in communications the different components. So the schematic as I see it is a little bit decentralized. So it's very flexible. You have one coupler that is one component of the climate model. The climate model looks more like a collection of different components, and the coupler adapts to different components and regrids and computes and puts in communication all these different components. And this reflects a little bit the development process of EC Earth that is very decentralized. And this is opposed as to a climate model like ICON. So ICON is developed in Germany and is in the Max Planck Institute, and it's more of a centralized structure. So all the components of the ICON model were designed, thought, and developed with the climate model in mind. So the interface is unified. There is a centralized model that governs the computational fluxes and the time stepping of the model. And this, of course, has some advantages, but loses the flexibility that a model like EC Earth has, where you can swap in and out different components. So these two approaches are completely valid, both of them. They reflect a little bit the development process of the climate model, and have different advantages and different disadvantages. And of course, if we want to have a framework to couple different components that has a generalized, centralized model that computes the fluxes, we need to take a little bit of both. So that was the idea. We need to have a model that is flexible, but is also centralized in a certain sense. And the nice thing is that this is possible with multiple dispatch from Julia. You can always adapt you can always have a centralized model that adapts to different components through multiple dispatch. So this is kind of a solvable problem. And this is what we want to achieve in terms of interface. So we want to take the already successful recipe from oceanography and speedy weather of having a generalized model that takes in different parameters or different components, different schemes, different parameterizations, and the model will change depending on what parameters or parameterization you pass to the model. So we want to have an Earth system model, a centralized structure that takes in different components, ocean, atmosphere, and sea ice, and unifies them all in one central structure. And it's very important that we expose the interfaces to the climate model, because the climate model needs to be the one that computes the fluxes and redistributes it through the various components. So this is the vision. This is what we want to achieve, and we haven't achieved it yet because the scope changed quite recently. So this is where we want to go. But given this vision, I want to show you just where we are right now. So what ClimaOcean can do right now. So one of the most important features of a climate model is regridding. So different components can be on different grids. So you want to be able to interface different components through a regridding process. And the idea of this framework is that the couple model will govern this regridding, but the couple model should also possess its own independent grid. So the idea is the couple model takes the information from the components, regrid them on the couple model grid, computes all the fluxes, and distributes them to the various components. In this way, you can keep the flexibility, but also have the centrality of a model that computes its own surface fluxes. And regridding in itself is kind of a trivial idea because it's just a sparse matrix multiplication between different quantities. The problem is that the regridding needs to be conservative. So you want that the integral of a certain quantities on the component grid and on the coupled model grid should be exactly the same. Otherwise, you start leaking energy and mass out of the system, and that's something that you don't want. So the problem here is computing the weights. That's the only problem of regridding. And especially since in ocean modeling, we really use kind of unorthodox grids. So an example of what we use is the grid on the top right. It's called the tripolar grid. that solves the two problems that we have in ocean modeling. So because of the algorithm that we chose, our grids are supposed to be locally orthogonal, unfortunately. We can change this, but we just didn't get to change it. And we have to avoid the singularity at the North Pole, because North Pole is in a place where you have the ocean. So what we do is we take the North Pole and we just stretch it out in two different singularities that are embedded into Canada and Russia. So we still have a singularity problem, but it's hidden in land, so we don't care about it. So this grid is probably the most simple grid that you can have that solves this problem. Otherwise, you have the cube sphere that is also quite complicated because you have all different local orthogonal systems that you have to take care of. So we didn't really develop yet weights computation framework, but at the moment we use XSMF, that is a wraparound the famous ESMF coupling package. But we're really stoked for using the conservative gridding package that Anshul is developing. So as soon as that's ready, we're going to have conservative gridding that is fast and will work perfectly in this framework. So the next thing that a couple model needs to do is to compute exchange fluxes. So at the moment, what we have assumes that a flux of a quantity phi can be expressed as a product of a characteristic velocity scale U star and a characteristic tracer scale phi star. There's not a strict requirement, but it's what we have implemented right now. We really want to expand this framework to make it more flexible and to be able to accept different formulation of surface fluxes. At the moment, we have only two formulations implemented, one very simple fixed coefficient fluxes where phi and phi star and U star depend on coefficients that you pass to the model that can be spatially varying or time varying. And the standard Monod-Nabokov similarity theory that assumes that a quantity is logarithmic as it moves away from the interface. So you get this kind of complicated formulation that has been derived from wall-bounded turbulence theory. So it's not really exact in the framework of interfaces in climate models. So models typically put a correction to this formula that is that psi function over there, which is extremely empirical. Basically, you have campaigns of experimentalists that go out in the ocean and just measure the air, measure the ocean, and invert this formula and take out that psi function. So there's a lot of space for improvement when it comes to surface parameterizations in climate models. And I think that this will be a framework a field in which data-driven parameterization or machine learning would fit actually very well. And this similarity theory formulation ends up producing a set of a couple of nonlinear equations that you need a solver to solve for. And at the moment, we solve for these quantities with a fixed point iteration solver, very simple. We have plans to improve it with something a little bit more advanced, like a multivariate secant method, but not more than that probably. And the important thing is that as part of the nonlinear solve, we include the interface quantities. So that phi I is temperature or salinity or humidity at the actual interface between different components that is computed as a balance of fluxes with the incoming fluxes from one component and the outgoing fluxes from the other component. And these phi quantities are really properties of the coupled system. They don't live in one component or another, but they belong to the coupled system. And I think they underlie the fact that you really need one overarching coupled system that governs the interfaces. Okay, a framework to handle climate data. So a big space in the source code of CleanMotion is dedicated to handling climate data. And this is because when you start doing realistic climate simulations, well, you need to force your components with prescribed data, or you need to initialize your ocean or your sea ice or your atmosphere. You need to validate the data you produce with climatology. So it's important that you have a way to retrieve and inspect climate data. So we have built this framework that is based on the metadata abstraction, that is just a lazy representation of a certain data set that can live online or can live locally, can live wherever you want. And this metadata will implement methods to download and retrieve the data from wherever it is located, and will interact with Oceananigans field and field time series type to materialize the data on a grid or on a grid in time, so that we can handle directly interpolation in space and time through this framework. At the moment, we can handle only gridded data because our in-painting methods are very, very primitive, and we only do linear interpolation. So it would be nice to see if we can extend this framework to use, I don't know, maybe satellite data or some more complicated scatter data that we can use to improve the models. And here there are some nice videos of the JuliaEO26 surface temperature, that is the atmosphere that we use to force the OMIP simulation. The sea ice concentration from the ECHO dataset, ECHO4, and sea surface salinity from the EN4 reanalysis dataset, all regraded onto Oceananigans fields and field time series. Okay, so I want to give you a little bit of an idea of how this coupled framework works. So for the moment, we try to keep it as simple as possible. So the whole flux computation happens on the coupled model grid. So the coupled model needs to know what state variables to take from the components and where to insert the already updated fluxes. And this is done through the component exchanger type, which needs to be extended for each other component that you insert in the climate model, and will inform the interpolate state and update net fluxes function on how to take the state variables, how to regrade it on the coupled grid, and how to insert the updated fluxes. And of course, the coupled model also needs to know how to time step the component. At the moment, the workflow is that the coupled model time steps all the components, updates the fluxes, and then you time step again. But we're trying to figure out if there's another way to couple the components more tightly. So maybe, for example, if different components use an RK3 substep or multi-stage time steppers, how to couple in between stages and not only at the end of the time step. Okay, so this was a little bit an overview of what we can do now with CleanMotion, and I want to show you now some examples of some simulations that come out of CleanMotion. So this, I think it looks pretty beautiful, but it's a very, very simple simulation to do with CleanMotion. This is the OMIP simulation at 1/6 of a degree. So it's a dynamical ocean with coupled to a dynamical sea ice model forced by a prescribed atmosphere. And I like to call this a GCM in 13 lines because it's the parallel to the turbulence in 7 lines example that we have in the README of Oceananigans, which is the simplest possible simulation that you can do with Oceananigans. Well, the simplest possible simulation that you can do with CleanMotion is an OMIP simulation. And this is a 2-component system because only the ocean and the sea ice are dynamical. The atmosphere is prescribed, so it does not really feel the effect of the fluxes from the ocean and the sea ice. But the structure is similar to an Oceananigans simulation, so we have a centralized model. In this case, this is called Ocean Sea Ice Model, which is a misnomer, so we also have to refactor this to something more like climate model or system model. And this accepts 3 components: the ocean, the sea ice, and the atmosphere. And the framework for handling data allows you to download and initialize the ocean state and the sea ice state from ECHO metadata. We could have chosen other data sets to initialize the data. Now, this simulation is very simple because it's only 2 components. These 2 components are on the same grid, which is the same grid that the coupled model uses. So there's effectively no regridding going on except for interpolation from the atmosphere. Now, the next logical step from here was to actually add an atmosphere. And the most logical atmosphere to include at the moment was PD weather because it's very simple to use and to interface with the coupled model. So this is a 3-component system. So it's an atmosphere, a primitive wet model from Speedy Weather, hydrostatic resurface model from Oceananigans, and a CS model from Clima Sea Ice, all coupled together that react one to another. The interfaces are computed with Monod-Nabokov similarity theory. So to be honest, this is not really a 3-component system. This is probably a 4-component system because Speedy Weather includes its own bucket land model. But since it's not part of CleanMotion yet, I wouldn't want to consider it as one component. And you can really see how baroclinic eddies that start developing in the atmosphere really exert stress on the sea ice and a momentum in the sea ice and in the ocean. So this example is still a little bit simple because the ocean and the sea ice are again on the same grid, which is the same grid as the coupled model. So I want to show a last example in which this is not the case. And this is trying to include another ocean model. So that is not even written in Julia. So this is coupling Speedy Weather with the Veros ocean model. That stands for Versatile Ocean Simulation. That's an ocean developed at University of Copenhagen, is probably one of the most usable ocean models after Oceanigans. And it's very easy to interface in this framework because it's written in Julia, and in Julia we have Python call, which is a very easy framework to exchange information between Python and Julia. So actually this was just, this was very easy to do. In a couple of days, we just coupled the Veros ocean model. And I'm actually very satisfied of the result because it demonstrates how flexible the interface can be. So going forward, the idea for this year is that we need to refactor the package. So ClimaOcean doesn't make much sense. Ocean CS model doesn't make much sense. So we have to refactor the name of the types and of the package. We need conservative and distributed regrading. For that, we'll use conservative regrading.jl. And we have to figure out a strategy for distributing the coupled simulation in on different workers. We need a land model. We cannot just use the speedy weather one. So we want to introduce a more full complexity land model. We can probably start with a simple one so that we start developing the interface between the land and the different components. And we want to run couple simulation to test the difference between a prognostic and a prescribed atmosphere. So I'm looking at this a little bit more from the ocean perspective. So I want to see how the ocean currents change when you put a prescribed atmosphere or when you have an atmosphere that feels the feedback of the ocean. And my dream would be to add support for Fortran models because, like it or not, that's where the development is in the climate modeling space. Most models are written in Fortran. So if we open a door for Fortran models to work in a couple of framework in Julia, that will probably attract many more users to a Julia coupled model. So yeah, that was all I had to say. Thank you.
Thank you. That was a wonderful talk. 2 questions. Have you considered Climate Earth instead of Climate Ocean, since you're probably going to include land also, at least, otherwise it gives the impression that, okay, it just models the oceans. If you want to model the interaction with the atmosphere in Earth, forget it, go somewhere else, which is not good. So the second question was, given the difficulties you mentioned with the surface interaction model, and I know a lot of the error by meaning unknowns in the climate model have been exactly how does Earth interact with oceans and how fast do trees and the ocean life reacts to changes in temperature and changes in acidity, and so basically the reaction mechanism of Earth. So have you considered just doing an integration over all possible parameters and values to try do a little bit of reverse engineering, instead of saying, okay, if you put these values to get this change of temperature, you say, okay, we have this change of temperature, what are the ranges of values that could explain this? And then look into it. Thank you.
So the answer to the first question is that Klima Earth already exists. So it's actually the couple model of the Klima project. So I don't really want to step on the toes. Like we need to separate we need a separation of concerns. So Klima Earth is just the actual Klimatmos, Klimaland, Oceanigans, and Klimaseis all together. So this is more of a framework where you can really just test new ideas when it comes to different components or different surface parameterizations, or you really want to focus on the sea ice and add a prescribed ocean and prescribed atmosphere on top and see how the sea ice changes. That enables you to interact with different components without necessarily being like one monolithic climate model like Klima Earth is, for example. And for the second question, it's a really good point. The idea, well, what I would like to do is to calibrate the parameters of the surface fluxes to match with data. So do like not really hand tuning, but automatic calibration. You can use like methods like ensemble Kalman inversion, and then you really find these parameters that give you the best results in terms of the actual state of the atmosphere and the ocean and the sea ice. So that will be a really good project to do. It's quite difficult because the whole system is very, very heavy. So doing an automatic calibration it's a very hard computational task. But for this reason, at least for our components, we're trying to make them as fast as possible so that we can do this inverse problem.
Hey, thanks for a great talk. Really excited by this. I wanted to, as you know, there's this climate models GL framework that I've created with a lot of the same goals, but I really started from the other end, right? So I built interfaces to, in fact, shenanigans and Python models and all of this. I haven't really focused on the coupling part yet, but I think there's going to be an interesting synergy or complementarity between those two things. The interface that I'm sort of putting forward is much more like the old school models, again, with the sense that that's a good way to attract people into our business. My question really was something slightly different, which is, I'm kind of surprised that you decided to do all of the data merging parts inside, like the data dependencies, and because or the regrading. I mean, there is an ecosystem of these things in Julia. Mesh arrays, for example, is something I created to do the regrading part. But there is also, so I'm surprised by this. Kind of, how do you guys choose what is kind of internal versus more modular and external? Is my question.
We depend on mesh arrays because we one of the data sets we have is Echo Darwin. Echo Darwin is on the lat long capped, so we need a way to regrade it, and there is no problem of depending on other packages that would do the regrading for us, for sure. But then we need to expose the data for I mean, it's good to have a way to visualize and to handle the data internally, because you need to validate, you need to force for example, if you have a prescribed component, you need the data that forces that prescribed component, that populates that prescribed component. So you need to have that data in your model. And if you need to have that, well, then you can expand to other data sets, because the idea is to create a framework that allows you to handle the data. So if it works for one data set, it can work for several. That's the idea. And there's no problem depending on other packages. If there's packages that do regrading, I'll take them. There's absolutely no problem with that.
There is something in mesh arrays that you might be interested in, which is recent. I added the NemoGrid support. And the NemoGrid support is this bipolar grid you guys have. Yeah, it's basically the same you have, right? The two poles. So we might be a step closer to being able to support that. But if I can just follow up on my question in reverse, I'm surprised, for example, that seawater polynomials is not an explicit dependency of shenanigans. To me, that's an obvious sort of thing to have.
It is.
It's explicit.
Yeah.
I found myself kind of having to be using one and using the other.
You need to use it when you want to. So that the TOS 10 equation of state is not an explicit dependency. It's not exported by seawater polynomials. Probably we should export it.
Oh, okay.
It's just specifically a TOS 10 equation of state that is not exported by seawater polynomials.
Okay, it would make my life easier because we can export it. I have an extension to shenanigans in climate models GL. And now I need to figure out how do I get the equation of state.
Using seawater polynomials.tos10, but we can export it for sure.
Sounds good. Anyway, thanks a lot for the great talk again.
So I don't work on global models, but I do also work on coupled models, and some of them are in different languages as well. So at our institute, we're using the basic modeling interface from the CSDMS, and it's just for you to know. Like I made the Julia version of this interface now, and I have some code, for instance, as well to from Julia run Fortran models like ModFlow through the C API. So I'd be happy to chat about that.
That's amazing. Yeah.
I have no idea, like these Fortran models that you're looking at, how feasible it is, for instance, to build them in Binary Builder.
Yeah, I guess you should build a library that exposes like the time step function in Fortran to Julia.
Yeah, exactly.
Yeah, so that's why I want to talk with Gael, that as an expert in MIT GCM, if he has an idea on how to do this.
So this basic modeling interface is of course not designed for Julia, so it's a bit less flexible in a way. And so I think you have more options. But yeah, still we can chat if you. Yeah.
For sure. Thanks.
Thank you for a great talk. So my question is, you're talking about coupling and enforcing. Have you done any thoughts about data assimilation? Would it be possible to assimilate data into some of these models?
Well, a big part of this project, is to try to make the model differentiable. So once we will be there, the idea is to calibrate automatically the model. So basically do data assimilation, or in a sense. That requires the model to be fully differentiable. Well, we can do it with other methods, but the idea is to make it differentiable. So there are bits and pieces in place, but the road is still long ahead. But definitely that is the path that we're following, to try to get a differentiable model that can assimilate data or can learn from data, which is basically assimilate data.
Thank you.
Mm.